Good afternoon. My name is Peter Campbell. I'm working with ALANA, Rebecca, and FABRICE. Unfortunately, David was not able to make it. He's had prior engagements. We are the fluctuating spatial distortion constants. Today we'll be showing you how to find angular velocity and acceleration. We'll also be showing you how to find velocity and acceleration of the tangential components and how they are dependent upon the radiuses.
Hello, I'm Rebecca, and I'll be explaining to you our diagram. This is the diagram of a record player that we used in our demonstration, which will be shown to you towards the end of this video. Here we have two different dots, a green and a red one, denoting the different Lego men, and then here is just a line showing our radius. And here are the three different radiuses. This one represents the record player, this the Lego Man 1, and Lego Man 2. Also, we have the components of angular acceleration and angular velocity, as well as the components of velocity tangential.
Hi, my name is Alana. I'm going to explain to you the process that we use to find all of our different constants. So first, we need to find the angular acceleration and velocity of our record table. To do this, we're using one of our constant acceleration formulas. The first thing we need to find in this formula is the degree at which our record player gets a constant omega. So we measured that and we got pi over 2, which is 90 degrees. The next thing that we do is we need to find our omega final, which we do by finding d theta over dt, which is the change in theta over the change in time. We also calculated that out and it came to 3.59 radians per second. So plug all those into the formula and we solve for our alpha, which is our angular acceleration, and it came out to 4.1. So overall we found an alpha of 4.1 radians per second squared and an omega of 3.5 radians per second. Next, we find the acceleration of each Lego man, which we do using our acceleration in the tangential direction formula, which is alpha multiplied by the radius. For our first Lego man, we have a radius of 0.04 meters, which comes out to create an acceleration in the tangential direction of 0.164 meters per second. Next, we do the same thing for our Lego man number 2, which had a radius of 0.105 meters, which gives us an acceleration in the tangential direction of 0.305 meters per second. Next, we're going to find the magnitude and direction of the Lego man in both its velocity and its acceleration. So to do this, we're going to split our velocity into the tangential direction and the angular direction. So in order to find the velocity in the angular direction, we have to take our omega times our radius. So the radius for Lego Man 1, like I said earlier, was 0.04. This gives us a velocity in the angular direction of 0.1436 meters per second. To find the velocity in the tangential direction, we have to take our radius times our theta over our time, which gave us a velocity in the tangential direction of 0.1436, which is the same for both. Next, we find the velocity of the Lego Man. That's number 2. So we took the same formula and it gave us a velocity in the angular direction of 0.3769 meters per second and a velocity in the tangential direction of 0.37699 meters per second. Now we need to find the acceleration of each Lego man in both the normal direction and the tangential direction. For the normal direction, we're taking omega squared times the radius. The radius is the same, so it's 0.04 meters again. And this gives us an acceleration in normal direction of 0.516 meters per second. For this case, and for Lego Man 2, our acceleration in the tangential direction will be 0 because our record player is moving at a constant velocity, which means that there won't be any acceleration, making it 0. So for the acceleration in the normal direction of Lego Man 2, it came out to be 1.353 meters per second, and the acceleration in the tangential direction, like I explained earlier, will be 0 meters per second squared.
To conclude this experiment, we found the deceleration of the record player once it was turned off. We used the same method that we used to find the acceleration of the record player. Omega squared final equals omega naught squared plus 2 times alpha, which is our angular acceleration, times the theta final minus the theta naught. Our final velocity, because it was decelerating, is 0. Our initial velocity is the constant velocity since it was measured from the time it was instantaneously turned off. It's 3.59 radians per second. The angle that it took for the record player to stop movement altogether was 133 degrees. And being, again, our baseline was 0 for when we measured from. So we plug all that into our equation, and we get 3.59 squared plus 2 times theta times alpha times 2.321, which is 133 degrees in radians. And you get an alpha that is negative 2.776 radians per second squared. What that means is that the record player is slowing down. And again, alpha is angular acceleration. So the angular acceleration is negative because it is stopping. This is our demonstration model. Here we have the record player with our 2 Lego men at different radiuses. This one is at 0.04 meters, and this one is at 0.105 meters, and the radius of the actual record player itself is 0.14 meters. What we have here is the green tape. This green tape denotes the 0 position. This red tape denotes the pi over 2 or 90 degree position. I'll tell you what that pink tape is in a minute. So what we did to calculate our numbers is we determined that it takes about pi over 2 distance for the record player to reach its stable velocity. So as you can see from there, we would time it until the green tape passed the red tape marker, and that would give us the time, and we knew that it was pi over 2 radians to that distance, which gave us our omega. That way we could calculate for angular acceleration. Now, for the constant speed, for the constant angular velocity, we just let it run, and we waited for the green tape to pass this green marker here, and we counted for 1 rotation, which is 2 pi radians, and then we timed it, so we had an angle over time, which gave us our constant omega, or a constant angular velocity. For deceleration, we did this. We started it up, allowed it to get to a constant velocity, which we know because we've calculated that. And then as soon as the green tape would pass the other green tape marker, we would stop it. And it's difficult to demonstrate this here, but when we had a more precise measurement method, we would allow for it to accelerate, and as soon as it would cross there, we would turn it off. And the average position was this piece of pink tape here, which is about 33 degrees past 90, so that's 123 degrees. Actually 133 degrees, because it's 43 degrees past the red tape. So using that and the time it takes for it to decelerate, we were able to get the delta omega there, and we were able to show how long it takes to decelerate, which then showed our total angular deceleration.
Hi, I'm Fabrice. As you have seen, the angular velocity will remain the same, but tangential velocity is going to increase due to the radius. As the radius increases, the tangential velocity will also increase. So since we used the stopwatch and the tape, we were able to create some human errors in our experiment. Thank you for watching.